were discussing about this BOD, the biochemical oxygen demand, and then let us find out the initially in the beginning that we have said. So, there is a determination of one important thing, that is determination of BOD. The standard, let me do it by step by step. Say this is number 1, collect some 30 to 50 milliliter of wastewater sample. Remember this wastewater sample in a stoppered bottle, if required by the nature of the wastewater add distilled water or water without BOD of its own to make the solution up to 400 ml, up to 400 ml. Determine the dissolved oxygen in the mixed water almost at the same instant. Keep the stoppered bottle in a dark environment or cover the bottle with dark opaque paper, right? Opaque paper. Why it is done? Very simple, very small reason for that is that there are certain organic substances in water. Which are mostly of say algal variety, they can photosynthesize under normal lighted condition. So, if they are doing that, so they would add oxygen to the water. So, this is why this precaution is generally kept. Okay, opaque paper. Generally, for European standard, we generally say the temperature the temperature maintained in an incubator generally the temperature maintained in an incubator is about 2 20 degrees centigrade is 20 degrees centigrade, generally the temperature maintained in an incubator is 20 degrees centigrade, where the bottle is kept, where the bottle is kept. You make a note here, note 20 degrees centigrade refers to the average working temperature in the European cities or European states where the test was first introduced. For experimental purpose fitting to our condition, fitting to the Indian condition, the temperature may also be at 30 to 40 degrees centigrade, 30 to 40 degrees centigrade. Okay, 30 to 40 degrees centigrade. So remember, this is this is an important thing, particularly for European states. Sometimes we also reduce the number of days. So say after this is how it is kept. Then there is a 6th day. This is the 6th step is at the 5th day at similar instant, at similar hour and minute specification, the 5th day at similar hour and minute specification, the sample is the sample is brought out and tested for the dissolved oxygen again, dissolved oxygen again, dissolved oxygen again, dissolved oxygen again. So this BOD5 would then be known as dissolved oxygen, would essentially be higher in the first case, dissolved oxygen initial, dissolved oxygen final divided by P. This P is known as the dilution factor. This P is known as the dilution factor. So you can see this is dissolved. You can see here, which is DOI is DO initial, DOF is DO final, and this P is the mixing ratio. It is also called a mixing ratio, or mixing. This is basically a mixing ratio where P, for this case, suppose for example, P may be, as I have said, P is say if you are taking about 50 ml and you are making it to 400 ml. So this one is 1 by 8. So it becomes 1 by 8 times of the. So BOD becomes this basically, or for this case, it would be multiplied by 8. The reason being is, we just tried this dilution. The dilution is generally done so as to increase the rate of, so as to see that the level of oxygen goes down considerably within a particular time. Okay, within a particular time. Say, for example, here suppose DOI, say DOI is if we consider DOI as generally is, say we find DOI as 10 milligram per liter, and we find DOF as say 2 milligram per liter. So, this BOD 5 in such cases would be 8 milligram per liter divided by this one is 8 milligram. This is a proportionality constant only 1 by 8. So, it is finding at 64 milligram per liter. Okay. This is as simple as that, right. This is one test, this is one kind of test, this is seeded test, and there is another kind of test for BOD. We generally called it as seeded BOD test, seeded BOD 5. What is done extremely extra steps that is generally done is after the sample wastewater is collected, after the sample wastewater is collected, we mix water having oxygen demand of its own Note, in the first case, in the ordinary BOD test, note that in the ordinary BOD test, the water had no oxygen demand of its own. Okay. The water that is mixed, remember that to make the water to make it to 400 ml. So, 50 ml we collected, we made it to 400 ml. Those 400 ml, say 350 ml was water without having a oxygen demands of its own, without having any DO, or without having any oxygen demand, not DO, without having any oxygen demand of its own. But here we use some oxygen demand so that the decomposition can be initiated. The idea is to almost immediately initiate the decomposition reaction. Otherwise, if the BOD is very low in a sample wastewater, if a BOD level is very low in sample wastewater, suppose you generally have a water which is having a very low BOD of its own. So, in such cases you might find at the end of the 5th day there is no depletion of oxygen, because the reaction rate is so slow that no discernible change has taken place, no observable change has taken place. So, if you put BOD, a seeded BOD, if you just use some water having its own BOD, then in that case we find out that the reaction takes place at a faster rate, and we will observe that the oxygen the depletion of oxygen is at a faster rate, and we find a considerable decrease in the oxygen decrease in the level of oxygen in the water. Okay. So, this is why this is called seeded. This is the water having BOD of its own is known as seed, and the method is known as seeded BOD test. This is known as seeded BOD test. The experiment, the method, seeded BOD test. So, in such cases what we find out is, we can very well write is like this: BOD of the mixture into the volume of water, that body of mixture, volume of the mixture is equal to BOD W wastewater volume of the wastewater plus BOD of the seed, BOD of the seed and BOD of the seed and volume of the seed, right. So, in such cases there are other things that we can find out is Vm is equal to Vw plus Vd. So, you can find out one this thing here, 2 here, and as you can find out from here, this is, if you just can find out like this, we can say this BOD of the waste can be written like BOD or BOD of the mixture divided by Vm divided by Vw plus BOD S multiplied by Vs divided by Vw multiplied by Vm divided by Vm. I mean, just to write it like this, is this basically to bring in this. So, here all this can be written as BOD BODM divided by Vw by Vm is very simple. I mean, just it's not necessary, also you can find it out yourself like this. This is Vs divided by Vm divided by Vw divided by Vm. This is substituting the definitions of P. So, that is the wastewater divided by the mixture. This is BOD by P. This is BOD M by P. P, that is we did in the mixing ratio. This is divided by this one is BOD S 1 minus P divided by P. So, you can find out this is also you can find out from this that this can be also be simply used as DOI minus DOF divided by DO. Say this is this is DO DS demand DOS DOSI demand of the seed, dissolved oxygen in the seed initially DOSF into 1 minus P divided by P, right. We have not done anything, very simple, this is BODS, this is dissolved oxygen of the seed initial, and DO in the this is a final. So, we make a separate test for the seed. So, one is that wastewater and the seed mixture, another is only the seed. So, we find out the seed. So, we find out from this, we find out the BOD of the wastewater. So, we can find out the BOD of the wastewater like this. Okay. Having said this, this is all about there are few problems, we will deal with these problems later on. Just to go ahead with this, now next is first order. Say there is BOD modeling, then we are coming to this term here is that BOD modeling. Here let me tell you this here, this is this BOD modeling. If you can see now, what happens is this for most cases, as I have said, if you just observe that this one is, if you just observe here that as I said that the dissolved oxygen would be reducing like this, dissolved oxygen DO. DO would be dissolved, this is DO with time. We can find out one standard relationship here, which would be this is, as I have said, like this is what would be, this is this oxygen BOD, this is on the other hand the BOD would be like this, on the other hand the BOD would be this is the complementary of that, complementary, and this would be finally the saturated value, saturated oxygen, saturated oxygen in the water. So here if you just say, if we just take a breather from here, we will try to see that it is in the first case of BOD modeling, this is quite interesting to observe. This is BOD modeling, this is first order reaction rate modeling, this is first order modeling. Generally first order modeling, what is done is, what it says is that it is assumed that the rate of decomposition of organic matter, the rate of decomposition, remember this, the rate of decomposition of organic matter is proportional to the amount of waste waiting to be decomposed, waiting to be decomposed in the wastewater, waiting to be decomposed in the wastewater. If we say this, if LT is equal to represent the amount of oxygen demand left, that is signifying the amount of waste left, and signifying the amount of waste left after time t, after time t, then first order reaction rate, first order reaction rate can be written as dLT divided by dt minus k into LT. Okay, minus k into LT, So what it says is k into LT is that it's also the minus is signifying that it is also already a decreasing function. It should be always continuously decreasing. The rate would continuously decrease. This is what it signifies, LT minus k into LT. Now here this one needs a certain kind of investigation. This particular reaction rate, this is particularly true, this is particularly this is one aspect only. Suppose if you see now that okay, here you can see this. This is, if you just observe, as I have said, say if we are just considering LT here, LT, and this is time. See here, this is particularly a plot which it talks like this, which it talks like this, where it says that the rate of depletion at any point of time in an exponential distribution, as you know, is a say if it is e to the power minus say some constant into t, in such cases that constant remains constant throughout the through the line of the plot. So, at any point of time the rate of change would remain same. This is mostly the typical thing that we generally observe, but generally is also in the very important thing here is this has to be understood. It is not necessary that all organic substances would follow this plot. Here we can observe, as we have said, this is there will be plot like this, there will be situations like this where it would be further plotting like this. So, in many cases, though the first order reaction rate is known as, it is written, in many cases it can be written as LT NT dt is equal to, if it is just k, if we just consider k, if we are not trying to change this k as a time related function, we can also at least write it like this as a power. This is in the form of say alpha. This alpha for these cases, as you can see here, it can be 1, it can be half, it can be 3 by 2, it can be 2, like this. It can be sometimes it can be 1 by 4, like that, depending on the nature of the waste, depending on the nature of the waste. All right. So, it is not necessary for all of you, for all cases, to find out a first order reaction rate modeling, and the first order, when it is considered as a first order reaction rate, then we can see this one would be in the form of an alpha. It can be also, it is not necessary that it would be a LT power 1, it can be different power also, depending on the nature of the waste, Okay. Now, having said so, we can see now that this, if we just try to do it, if we just say in such cases, what we can think of is LT is equal to L0 e to the power minus k into t, or else as you can see, this can be, finally this is the derivation of it is very simple. So, you can see DLT LT, right, this is into k into dt, this is 0 to t DLT dt, sorry, LT, just 1 minute. Okay, just make this. Okay, now it doesn't go. No, this is all right. This is coming as, this one should go now. Okay. Anyway, so okay, let us not further waste time on this. We'll this, as you can see here, k to the power minus LT. So, from this we can further go on to say this, as you can, as or DLT LT is basically k into dt. So, is on integration this is 0 to t 0 to t dlt dt, sorry, lt. This is as an integration. Here it is this it would begin from L0 into t, Lt, L0 into t when there is no demand. Whereas there is no demand, this is this would begin from here, and this one is minus k kt as you can see here. So here it is log lt, this is L0 to Lt, and this one is minus kt, or we can find out that this would be essentially this is what we can find out. Lt is equal to L0 into e to the power minus kt. Minus, so it comes Lt, log Lt divided by log L0. So this one is, if Lt by L0 is would be e to the power minus kt, so L0 you are bringing in there, so L0 into e to the power minus kt. So this one is, it says that at any point of time L0 is known as the ultimate carbonaceous. Remember this carbonaceous, ultimate carbonaceous BOD. This is known as ultimate carbonaceous BOD, which is nothing but is, you can see, log say Lt, this is log L0, or say this one is e to the power. So you can find out this. So this is log Lt divided by L0. So you find out like this. So here, as you can see, this one is the ultimate carbonaceous biochemical oxygen demand. Ultimate carbonaceous biochemical oxygen demand. So in case if we are just plotting it now, this this you try to see this. BOD remaining, and if we just put time here, BOD remaining, and if we put time here, this we can see that this one would be, this is going finally, as this is an exponential, this would be an asymptotic term. The modeling part, as you can see, this one is here, this one is BODT, this one is Lt, the remaining Lt. This is the ultimate demand at the start. So this is L0, ultimate demand. Remember this, don't confuse with this saturated value of oxygen. These are two different things. Okay, remember, don't confuse with saturated value of oxygen. Here it is, there are two different things. This is BODT, so this is Lt that you can find out BODT. This is the Lt plus BODT. So at any point of time we can also see L0 is ultimate biochemical oxygen demand is BODT plus Lt. So the demand already consumed plus demand remaining. It is ultimate carbonaceous oxygen biochemical oxygen demand. On the similar light, if you just observe this, this is oxygen consumed, oxygen consumed, so you can see this is what is, this is BOD T, this is LT, this is L0, this is ultimate biochemical, ultimate carbonaceous BOD. Right. So, let me again begin this discussion here. I mean, we will conclude here today, but as such, let me explain these things again to you. So, at the start you can see this is where, this is the oxygen depletion. If you just observe this oxygen depletion, if you can find out, if you just oxygen here, oxygen consumed, here this is, say this is oxygen consumed or oxygen level. Say oxygen, you can write out oxygen level, oxygen remaining or oxygen level or oxygen remaining. Oxygen level you write, oxygen level or O2 level. If this is O2 level, I am just plotting a different point here. It is not to coincide with L0. You can see this oxygen level would essentially decrease like this. This is oxygen level would essentially decrease, say from its saturated value, from the saturated value at that salinity, the oxygen level would be going to go down. This would be, it is going towards 0. Okay. All right. So, this is BOD remaining at the beginning, the BOD at the beginning there is no demand, because at the start there is no demand. As soon as more and more carbohydrates are used for decomposition, the rate of BOD remaining goes down, but the BOD essentially goes down steadily, but at the same time the rate of BOD also slows down as more and more BOD are consumed. And as you can see here, that is, in the oxygen consumed here, or oxygen level at that point of time would begin to decrease also. That means, there's a reciprocal of this. If a reciprocal of this can be drawn here, this is what it is generally observed like this. So, oxygen consumed, or it is the oxygen level. So, this is what essentially takes place in water. Now, there is one important assertion here I just want to make. This thing is very important for all of us. This is mostly takes place when this is particularly this kind of plots are, these guys are plots are true and particularly important when there is the waste is of biological or biochemical in nature. Waste is of biochemical or biological in nature, but it is not true or not applicable. Essentially, never use not true and not applicable in case of inorganic wastes, in case of inorganic wastes, in case of inorganic wastes and inorganic and non biodegradable waste. This is also biodegradable waste. Right? In case of waste is of biochemical, biological or biochemical in nature, biodegradable waste, and in case of inorganic waste and not, it is not applicable. This particular modeling is not applicable. So, this is not applicable. What is important in such cases, in cases particularly there may not be any demand of oxidation, there may not be any demand of oxidation of an inorganic substance, right. Organic substances have a demand, because this particularly the microbes have a demand for biochemical wastes, because for their food they use it, but generally in metals, say inorganics, there is no necessity, there may not be any necessity for the microbes to decompose it, and using oxygen. Remember, when it can decompose, it may not require to decompose with the help of oxygen or in the presence of oxygen. So, in such cases this is not absolutely. What is more important in cases of this are the metal solubilities. We would see this in one of these classes, metal solubilities. These metal solubilities deal with this particularly the soluble in a partial pressure condition in water, how one metallic ion gets released in preference to another metallic ion, right. And in such situation we would see this, as I have said, in many cases the speciations become different. Just let me give you a simple example here. This may give you a simple example here, where we could observe this particularly this metal solubilities. If you just see this metal solubilities here, you can see this, say, as you can see, mostly dissolved molecules of inorganic substances break into charged ions, break into charged ions, right. Break into charged ions. These charged ions, you can see this is charged ions is cadmium. This is quite interesting to observe that cadmium in the presence of chlorine ion can form a reversible reaction of CdCl. See this, CdCl plus, it can also say CdCl, this CdCl plus would be then Cl minus can form CdCl2, CdCl2 plus Cl minus can CdCl3 minus this CdCl3 minus can form with Cl minus can form say CdCl4, Cl4. So you can see this with just observing, we are just seeing that here cadmium can stay in water, can remain in water in 4 species having 4 different valencies. This is number 1, this is 1 valency, this is 2, this is 3, this is 4. In 4 valencies that interestingly all species of CD cadmium may not be toxic, but 1 or 2 species may be toxic. So we will use this in a different context in a different lecture. Okay, we conclude today's lecture by this. I mean, we will take up this issue of the first order BOD modeling again in the tomorrow's class. Okay.